The second postulate of quantum mechanics has to do with things that we can observe and operators. And so the postulate states that to every observable meaning something we can measure, so to every observable thing that we can observe about a system in classical mechanics, so this would be like Newton's laws and things like that, there is a corresponding operator in quantum mechanics. Now, we've already been introduced to a couple of these. If you want a not exhaustive, but a more complete list, you can see table 4.1 in your textbook. Or in the online textbook, there's a nice table there as well that's very similar in section 4.2. But we'll go through some of the most important ones. And so just to give some, why isn't this scrolling? So just to give some of these, I guess we'll leave that in the video. To give some of these, the position operator, or the position, right, of a system, not operate, but the position variable, observable. The corresponding operator is the position operator. And this is equal to just multiplying by x. So this is the simplest operator that we have. Another one that we've already seen is the momentum operator. So the observable momentum, p in, say, a single direction, p of x. The corresponding operator is the momentum operator, which we've already seen is defined this way. So negative I h bar, first derivative with respect to x. The most important one that we've already seen as well is the energy observable, one of our most important observables. The corresponding operator is the Hamiltonian operator, which is negative h bar squared over 2m. And I'll write the three-dimensional version, del squared plus potential energy. And I wrote just x, but I'll write that as x, y, and z. Okay, and so one final set of operators that we're particularly interested in is the angular momentum operators. So there are three different ones, technically four. So there's the overall angular momentum operator, and then there's those in each direction. So again, these are given in your textbook. I'll just write out just one example. I'll just do the Lx operator. So this is angular momentum in the x direction. And the classical version of this is it's y times pz minus z times py. And this has this form because this is a cross product. Even in classical mechanics, this is a cross product. So the quantum version of this is the angular momentum operator, Lx. And what we do is we substitute for pz and py. We use the momentum operator here and make a substitution. And so we'll get negative I h bar, which comes from that momentum operator. And then we'll end up with derivatives. So y derivative with respect to z minus z derivative with respect to y. And we get corresponding operators for the Ly and Lz that you can find in your textbook.